So we can take our discussion about vapor pressure and boiling points and their relationship and extend it a bit more to include melting and sublimation. We can do all of this by constructing what's known as a phase diagram. Phase diagrams are shown here where we always have pressure on the y-axis and temperature on the x-axis. And phase diagrams can be a little bit confusing to read at first, so let's just go through a few definitions and illustrate some examples of how we would interpret this diagram. So first is we'll note that there is a point labeled C on this diagram that's labeled the critical point. The critical point is simply the point that corresponds to the critical temperature and pressure. This is, remember, the temperature and pressure at which we can have a discrete liquid phase form, and above that in temperature we're unable to form a fluid or a liquid phase anymore. The phase that does exist at temperatures higher than that and pressures higher than that is one that's indistinguishable whether it's a liquid or a gas phase, and so it's simply labeled a supercritical fluid. Now there's also a point labeled T on this curve that is known as the triple point. This is the point at which all three phases are in equilibrium. So if the melting point is the point where the solid and the liquid phase are in equilibrium, and the boiling point is the point where the liquid and gas phases are in equilibrium, the triple point is that point where all three phases are in equilibrium. We may not be familiar with triple points, but we'll show one or two later on in a couple of specific examples. Now, just like we can have normal boiling points, which is defined as the boiling point at 1 atmosphere of pressure, we can also have a normal melting point, which is again simply the temperature corresponding to the melting transition at 1 atmosphere of pressure. So if 1 atmosphere of pressure was somewhere here on the y-axis, we would simply trace this across until we hit the transition line that would indicate the phase transition, and then trace our way down to the temperature to get the normal melting temperature, or trace all the way across to the vapor pressure curve to get the normal boiling point. Now, increasing the pressure tends to lead to an increase in the sublimation temperature, the melting temperature, and the vaporization temperature. Because increasing pressure tends to push the molecules closer together, then it requires more energy in the form of increasing temperature to drive those molecules apart, whether to go from solid to gas or solid to liquid or liquid to gas. And we can see that illustrated in this generic curve where if we're at a very low pressure, say here, then we can trace our way across and say that sublimation will occur at this particular temperature. But if I increase the pressure, then sublimation, if I trace my way across, occurs at a higher temperature value. The same thing for solid going to liquid for the melting point. If I'm at this particular pressure, it takes a certain temperature to melt, but if I increase the pressure, then the temperature for melting increases as well. So let's go through a couple specific examples of phase diagrams. So here's a phase diagram for CO2, and we see the critical point is at 31.1 degrees Celsius, 73 atmospheres of pressure. Above that is a supercritical fluid at temperatures and pressures greater than that value. And we have our triple point at negative 56.4 degrees Celsius and 5.11 atmospheres. Neither of these are standard conditions, so we probably wouldn't encounter the triple point of CO2 outside the laboratory. And if we want to look at just a few normal values, normal boiling point or normal melting point, well, if I look at 1 atmospheric pressure and trace my way across, what I will see is that I only encounter the sublimation curve. So at normal atmospheric pressure, at 1 atmosphere of pressure, there is no normal melting point and no normal boiling point for CO2. CO2 does not melt or boil at 1 atmosphere of pressure, no matter the temperature. It can only sublime from the solid to the gas. And if you've ever gotten CO2, it's a solid. You can buy it sometimes from stores and leave it out. It doesn't turn into a liquid phase. It will condense water certainly from the air, but it itself slowly just sublimes into gas. If we look at the phase diagram for water, we can also note a few things. So here, the critical point at 374 degrees Celsius and 217 atmospheres. It's unlikely we will ever see that. And if we ourselves were under that type of pressure or temperature, we would certainly be dead very quickly. And also we can see why we've probably never seen the triple point, because the triple point occurs at essentially 0 degrees Celsius, but also at such extraordinarily low pressures that we would not see those under normal conditions. We can look at the normal melting point and normal boiling point by going to 1 atmosphere of pressure and tracing our way across, and we'll see we intersect around 0 with the melting point, and then if you keep going, we'll intersect around 100 for the normal boiling point. There are a couple other things to point out from this particular phase diagram. So one thing is that we have an unusual slope for the melting curve. The melting curve slope is slightly negative, which means that if we increase the pressure, the temperature for melting actually decreases. This might seem a little bit strange since it's a little opposite of the normal cases, but if we remember our discussion of the density of water earlier as a liquid and a solid, maybe it makes a little bit more sense. So this type of negative slope for this only occurs for materials whose solid phase is less dense than the liquid phase. Remember, in the solid phase for water, the molecules are actually farther apart from each other than they are in the liquid phase. So if you increase the pressure, you're simply pushing the molecules closer together, which is what they would be like in the liquid phase anyway. And so increasing the pressure actually decreases the temperature required to melt water in this particular case. But again, this is only for materials where the solid phase is less dense, where the molecules are farther apart in the solid phase than they are in the liquid phase. All right, let's take this information and try to apply it in a few examples. We have some phase diagram that we've been given for a hypothetical substance, and we're asked to estimate the normal boiling point and the normal freezing point for this substance. Well, remember that the freezing point is the same as the melting point, and normal means that we're at 1 atmosphere, so that's up here on the curve right at this pressure value. So I trace my way across until I encounter the melting and vaporization and vapor pressure curve. So trace my way across and I intersect the blue curve right here at maybe, if I trace my way down from here straight down to the temperature, I say maybe I'm at about 260 degrees Celsius. It's an estimation, but that, or not Celsius in this case, Kelvin, 260 Kelvin. The boiling point, I simply trace over until I hit the vapor pressure curve and then bring this down. I would say, oh, my boiling point occurs maybe at, say, about 360 or 365 Kelvin. Now, I can ask what is the physical state of the substance under certain conditions and simply find those values on the graph and then detect which region they exist in. So temperature of 150 Kelvin and pressure of 0.2 atmospheres. Well, 150 Kelvin is right here. 0.2 atmospheres, well, half of 0.5 is 0.25, so that's about here. So 0.2 is maybe at around this region right here. I can use my pen to illustrate. So maybe I'm about here. I'm about at 150. So I intersect those. I would say at that intersection point, I am probably in the gas phase for that substance, where gas is kind of the tan color. At 300 Kelvin and 1 atmosphere, so 300 Kelvin's right here, 1 atmosphere, we've seen that before. That places me approximately here, solidly in the blue or liquid region of the phase diagram. And so I would certainly be a liquid at that temperature and pressure. Then finally, I'm asked, what's the triple point of the substance? The triple point is where all three curves intersect. The sublimation, the melting, and the vapor pressure curve all intersect. So that is this value right here, which occurs slightly under 0.5. Maybe we're at 0.45 for the pressure, and we occur just slightly below 200. Maybe we're at 180 here. So maybe the triple point for this substance would be at about 180 Kelvin and about 0.45 atmospheres. Again, this is just an estimation, but hopefully it illustrates for you how we use phase diagrams and how we interpret them.